So hello guys, welcome to my channel. Today let's see what is a background noise and brightness temperature. So basically a background noise, we'll see an antenna noise power may be received from external environment or generated internally as thermal noise due to losses in the antenna itself. So basically there are antenna noise will be classified as two types: external noise or internal noise. External noise is caused by environment, internal noise is caused by the equipment or the antenna itself. So while noise produced within a receiver is controllable to some extent. So when I told you before in the previous lecture that if it is a noise that is generated internally, so that noise can be controlled. You can control that noise, okay, by using a proper equipment or proper material. But the term that which is not able to control is external environment. So because it depends on the environment, you can't control the environment, right? So that's what. And may exceed, so sometimes this external noise or the noise due to environment might exceed the threshold levels, okay, noise levels of the receiver itself. So this is the, so thus it is important to characterize the noise power delivered to a receiver by the antenna. So this is the one of the term we need to focus on. This external noise should be, we should consider it as some one of the main parameters. So let us take an antenna. So this is an antenna. The so some radiation is sent. This is an basically this is a radiation pattern is looking like this. So there will be a main lobe and there are some few minor lobes on sides. Okay, this radiation is going into the atmosphere. Okay, so while it is going to atmosphere, the atmosphere will have the temperature T. Okay, let us take that is the sky, because the sky has a temperature T. So we know that in my previous lectures, that is on noise chapter, we can see what is the noise power that is generated when the temperature is T is there. That is N0 is equal to KTB, right? So that's how we wrote the noise, how much noise power will be generated when there is a temperature of T. So KTB. Okay, so some typical background noise temperatures that are relevant to noise low microwave frequencies are as follows. So basically these are some background noise. These are the background noises, okay, or the external noise we can say. So this background noise or the this is caused by temperature, due to temperature, right? That's why background noise temperature we call it as, okay, call it as background noise temperature. So that are relevant at a low microwave frequencies are as follows. So when basically the environment can be classified as three ways. One is sky, when we are pointing the antenna towards zenith. That means towards zenith means basically if you take a hemisphere like this, you are at a center and you are looking at the top. So basically this is called zenith. And horizon in the sense the horizontal, what you call the land, okay, not ground. Basically we can say like a horizontal direction, vertical direction, like this, you understand? So when you're pointing the antenna towards up, it is zenith. When you're pointing towards like if an antenna is placed like this, so this is horizon, okay, this is called horizon. When it antenna is placed upwards, okay, this is zenith. That's it. So what is the difference between these two positions? So when you observe the layers of atmosphere, when at zenith, basically it is the topmost layer, where then basically when you, as the altitude increases, the temperatures drop down, right? That's why on the top hill edges we'll see there is it is too cool. So the same reason why we got here at zenith the temperature is 3 to 5 Kelvin. See how much low, it's nearly near to 0 Kelvin only. But we know that the noise power is directly proportional to temperature. So the temperature here is so less, that's why noise will be also very less while when you point to zenith. But when you point to horizon, that is horizontal direction, basically that in that it is a normal sky level, okay, in the sky level, this is sky and this is a ground. So when the antenna is placed on like this on in the sky, then along this is the so thick, right? Basically it will be like thick a thick layer. So in this thick layer we are placing an antenna, and then it is transmitting like this. So in this, actually in this layer, the temperature is might be around 50 Kelvin to 100 Kelvin. So the temperature is high, so the noise will be also high. And when it compared to ground, okay, when the antenna is at the ground plane, when the antenna is kept at ground, then uh, here the temperature is around room temperature, that is 290 to 300 Kelvin. So even more the noise will be very high here. So that's why basically we most concerned about horizon and ground, because there are significant noise power that is generated compared to zenith. Okay, the ground plane noise temperature increases as the antenna is pointed towards the horizon. So basically we can see what we 1 minute. Uh, so what he is saying is, for example, let us take, this is the ground and this is the reference point. So this is the reference point. We are moving around, or we can say like this, we can move, rotate, anyway clockwise or anti-clockwise, doesn't matter. So or let us say this is the reference 0 degrees and this is the point. I have moving this antenna towards up some 10 degrees, or okay, I'll with respect to the graph I'll tell. So 10 degrees, as then in 5 degrees also is there. So somewhere around here 5 degrees, and again one more is 90 degrees. Okay, so one is around along the ground. Basically the radar is the radar direction is along the ground, basically at 0 degrees, and I have raised the antenna 5 degrees with respect to the ground, this angle, and this is at 10 degrees, basically it is at 90 degrees. So when it is vertical, then we said that the temperatures will be low, that's why it has low noise power. So according to this, for example, if it is N01, N02, N03 and N04, the N04 will be greater than N03, greater than N02, greater than N01, right? Let us see whether we are getting these relation in the graph. So we can see when it is 0, that means N04, right? So that is having the high value, that's why it is on the top. So here we can see it is on the top layer. We can see it is in the top layer. And when the temperature, when the antenna inclination is 50 degrees, so somewhere here, so that is the graph is below this, right? And when it still, I have increased the angle to 10 degrees, is still below, and it's still below. You understand, no? Basically the noise is decreasing when you increase the angle with respect to the ground. Okay, so this graph is between background noise temperature TB versus frequency. Okay, here we can observe there are two spikes coming up, right? One is here at this point, and here one other point. So basically these spikes, why we are got these peaks, basically these peaks are caused due to molecules that are present in atmosphere. So these peaks are caused by a particular molecules. One is H2O and other is O2. Okay, water vapor will be there, no, in atmosphere. Due to water vapor, these peaks are this line, this first line. Okay, this is wait, this is because of H2O. This is because of O2. Okay, that's it. So basically this graph, while drawing this graph, they considered that the surface temperature at a surface temperature of 15 degrees and a surface water vapor density of 7.5 grams per meter cube. This is according to this, the ground is taken as a reference of sea level. So this is what we are taking, and from this, what we can mathematically we can write the background temperature. Okay, what is the background temperature here? So we can see basically when the antenna beam width is broad enough that different parts of an antenna pattern seem different. So background temperature, okay, seem different background temperatures. The effective brightness temperature seen by the antenna can be found by weighing the separate distribution of background temperatures. Basically in antenna there are different parts, right? So each part will have different background temperatures. So all the effective is called effective background temperature. We call that all the effective background temperatures is, so all the, when you combine all the background temperatures of antenna parts, okay, antenna parts, that is called effective brightness temperature. Okay, background and brightness, see the difference. Okay, so that's what. So basically what we can say, for example, let us take an antenna with a shape like this. For example, if an antenna is like this and there is somewhat small parts attached to it, this is an antenna where this part is generating one pattern, this part is generating one pattern, this part is generating one pattern. Each three different will have three different background temperatures. So so we call that background temperature denoted by T capital B. Okay, capital TB, where brightness temperature is denoted by small b, capital T small b. Okay, TB. Here we have to take all these background temperatures. Okay, all these background temperatures, and we have some integrating them. So then we'll get brightness temperature. That's it. So mathematically we can write it as this equation, where TB theta comma phi is the distribution of background temperatures, and d theta comma phi is the directivity of the pattern function or the power pattern function of the antenna. So theta comma phi, because it is in a spherical coordinate system, we are taking a spherical coordinate system, that's what. So that is what. So when TB is a constant, above equation reduces TB is equal to TB. So basically when we see the TB is constant, that means all these parts are generating same background temperature, then the effective brightness temperature will be the same value, capital TB only, T capital B only. Okay, so also note that the definition of an antenna brightness temperature does not involve the gain or efficiency of antenna, and so does not include thermal noise due to losses in the antenna. So in this expression we can see that there is no term related to thermal noise, right? So or gain, involve any gain, basically gain or efficiency of the antenna. So that's why it doesn't include any thermal noise. Okay, into this. Now coming to antenna noise temperature and G by T. So if the receiving antenna has dissipative loss, so that its radiation efficiency eta radiation is less than unity. That's what that means in practical scenario it won't radiate all the input power, right? That's what he's saying. So for that intercepted by an antenna, this reduction applies to receive noise power and received noise power also as well. That means here in the radiated efficiency is what? Input noise power. So input power is radiated outside. Now here in the receiver what happens, there will be some power received. That entire power received will not be entered into the circuitry behind, right? That means for example, let us take a device here, and this is connected to an antenna. Okay, this is an antenna block, or this we can say this is an antenna, and this is some device connected. So when something is input received power, when it is inserted into this antenna, not all the power will be some, suppose here there will be some loss, I will call it as PR dash, which will be less than PR, the same way how it is happened for transmitter. So in addition so less than, so this reduction applies to receiver as well. So the noise temperature of the antenna will be reduced by a brightness temperature by a factor eta radiated. So it will be decreased by a factor of eta radiated is that brightness temperature. So in addition, thermal noise will be generated internally by the receiver losses in the antenna, and it will be increase the noise temperature of antenna. So basically what happens, thermal noise will be generated internally, right, due to parts. This will internally due to resistive losses, and this will increase the noise temperature. Basically what happens, this will be added to normal external noise. This internal noise will be added to the external noise also, and that's why there will be an increase in the noise temperature of antenna. In terms of noise power, a lossy antenna be modeled as a lossless antenna, and an attenuator having a power loss factor of L is equals to 1 by eta radiated. So what he's saying is we can make a lossy antenna can be modeled as a lossless. We to model in the sense to represent it. Okay, so for example, let us take this is an lossy antenna. So we can model this as what he is saying. We can have this lossless antenna, some lossless antenna. Okay, lossless antenna combined with some attenuator. Like this also we can work. Let's say attenuator has a gain L, that is 1 by eta radiated. Okay, this is what we are telling. So this is what even though so we can represent in terms of lossless also, but we should add another block called attenuator. So basically the resulting noise temperature, that is resulting noise temperature is Ta, such seen at an antenna terminal fields. So Tb by L plus L minus 1 by L. Okay, into Tp. Now so this is like 1 by L is what L is what 1 by eta radiated, right? We substituted that here in this formula, we got this formula. So the equivalent temperature Ta is called the antenna noise temperature, and it is a combination of external brightness temperature seen by the antenna and the thermal noise generated by the antenna. Okay, this is the Tb is the external noise. This part is external noise and this part is internal noise, where Tp is the internal temperature internal noise that is caused by a temperature Tp. So observe that the above equation, if you observe that if the eta radiated is 1, then it is the noise due to temperature is purely due to external only, not due to internal. If eta radiated is 0, then it is the noise is totally due to internal, not because this term will become, this external term will become 0, right? So that's why only internal it will be. So basically this is internal and this is this is external and this is internal. Okay, the antenna noise temperature defined above is useful figure for merit for a receiver antenna because it characterizes the total noise power delivered by the antenna to the input of a receiver. So basically this is an important relation, so that it is actually defining how much internal and how much external noise is interfered. So another useful figure of merit for receiver antenna is G by T ratio. So G by T ratio is like G by T in terms of basically G by T ratio is the G is the gain of an antenna, T is the TA. Basically you can write TA. Basically TA is the antenna noise temperature. So in dB it is 10 log of G by TA, dB per Kelvin. Okay, so I think it's time. Yeah, so in the next video we will see what is the microwave applications. So thank you for watching. Like, share and comment. Don't forget to subscribe.